Hello, I'm Long. Are you responsible for a scientific equipment that stopped working and wondering what to do? Well, most repairs can be done by a layperson with some support. It'll be even easier if you have access to a standard servicing procedure or an SSP. So let's talk about it. The first thing to know about standard servicing procedures or an SSP is that it currently doesn't exist. When you buy a scientific equipment, many manufacturers will offer a service contract with an annual cost of approximately 10% the total cost of the equipment. When something goes wrong with the equipment, you call the company, they make their best guess of the problem, dispatch service technicians, and fix the problem. If you don't have a service contract, you can pay for on-demand service. The process is exactly the same, except after the company determines the problem, they will provide a quote with an estimate for the repair. The quote often includes line items for parts, labor, and travel. Labor can be estimated at roughly $300 per hour or $2,400 per day. The actual costs will be invoiced. The third, and in my opinion, the best option is self-repair. If a business can do it and make a profit, then repairing must be a process that can be performed by the technicians who may be new trainees or experienced veterans. From my own experiences repairing over 12 different types of scientific equipment, the majority of repairs can be performed by a layperson when they are provided excellent instructions. Self-repair is approachable because it is likely a natural law for things to be made of other things. Humans are made of organs that are made of cells. Cars are made of parts, which are made of atoms. This simplifies repairing to a process where you identify the bad part and replace it. Shown here is our 6-source magnetron sputtering system. This tool was acquired in 2008 where it was run and managed by graduate students who likely did a great job. We began taking care of it in 2009 when UHNF opened its doors. It took us many years to develop a professional laboratory operation, but in 2015 we began to develop a process for repairing equipment in the lab. The components pointed out here have all been replaced with used, refurbished, or new parts. Once you identify the bad component, you can replace it with an equivalent component. I often replace it with a used or refurbished component by searching the manufacturer and model number on Google. Sometimes the component manufacturer will offer to repair the component. Either way can get the tool repaired for a fraction of the cost of buying a new component. The most time and skill-intensive part is figuring out the problem. Typically, we have a conversation between a layperson and a technician. The technician will likely figure out most issues immediately if they are right in front of the tool. But it's expensive, so they need to figure it out through the layperson. This can take a while, depending on their combined communication skills and experience. I prefer to communicate via email. I try to explain to the best of my knowledge what I think the problem is and made it a habit to provide photos with annotations. For example, our heater system won't turn on, and I provided a photo of what the heater looks like. When the technician saw this photo, he pointed out that 1. Both lamps are not installed properly, which lead to poor cooling and early failure. 2. The thermocouple is missing a liner which can result in poor temperature control. And 3. The rainbow-colored reflector is a sign of overheating. Yep, we messed up installing these lamps and thank goodness we got caught. A risk of self-repair is doing it wrong, so it is critically important to communicate as clearly as possible. This means to provide photos with annotations to ensure that everyone is talking about the same thing. Mistakes during a repair may cause more damage to the equipment or change its performance that tend to go unnoticed. In this example, the sample temperature before and after the fix will likely be different. We explain this to our users with photos and annotations, so they know we messed up, we addressed the issue, and their recipe might need to be adjusted. Documenting the repair in an SSP ensures that this problem will never happen again. The mistake made in the last slide occurred because of ignorance and lack of repairing experience. Taking apart something is easy, but a successful reassembly requires everything to be put back correctly. This task is best performed when you have photographic memory. Fortunately, we all acquired this superpower when the smartphone was invented. Take a photo before you do anything. It will help when you need to return the thing to the way it was. For example, photo 1 and 2 show how the cables are connected. Number 3 shows the stage before it was moved, and number 4 shows the stage before removing the backplate. You do not need to know the important things in photo number 5, but you can try to match the photo when you put it back together. When taking something apart, you might run into a situation where a part feels stuck. Should you pry harder? No, stop right there. Pick up the phone and talk to a technician. Any mistake made during a repair will often lead to significantly more damage to the equipment. Most things are designed to be easily assembled and repairable, so if you have to use a lot of force, then something is wrong. Sometimes just putting everything back together is not enough. In this example, I spoke with the technician and learned that prior to disassembly, I need to measure the behavior of the XY actuator, then perform the same measurement after reassembly. If they don't match, then I need to mechanically tune the preload on the actuator to achieve the desirable behavior. Although I have never done this before, it took 4 hours to fix the issue. If I had to send it to the company for repairs, it would have cost 2 weeks and up to $2,500. I performed this repair 4 times over 2 years, so the value from self-repair can add up quickly. It is always risky to do something you've never done before, but once you've done it, performing the same repair may be trivial. However, you might not remember what you did the next time it happens. A good habit is to store all your communications, notes, and photos in a folder that your team can easily find in the future. If you have time, you can write a standard servicing procedure, a step-by-step guide to perform the repair. The SSP does not need to be perfect. I write as accurately as I can with the photos that I took. The SSP can always be improved the next time you perform the repair. Questions you have during the second repair indicates the need for better instructions. Initially, I wrote the SSP for my staff, or a person with some technical skills. In hindsight, it was a mistake since skills and experience vary from person to person. I am confident that with clear instructions, skill and knowledge is not required to successfully perform a repair. In fact, in December 2022, I was on the other side of the globe and the reactive ion etcher crushed the wafer. This is a common problem and the graduate student has seen me repair this, so I sent him the SSP and asked for a screenshot when he is done. He performed the repair correctly and the screenshot suggests the valve is not sealing well, likely due to wafer pieces on the valve seal. Thus, I sent him the SSP to remove the valve and clean it. He has never seen this before, but performed the repair flawlessly. I knew this would work because instructions in the SSP is far clearer than the emails and phone conversations that I worked with. It is far more comfortable or less risky to fix something for the first time with an SSP because it provides clear instructions with photos of every step. There is a lot more to maintaining equipment than repairs. It is very important to have parts and tools on site, or a repair kit. If you don't have one, build it as you go. A plastic compartment box is perfect for organizing a repair kit. I use an electric hot knife to cut the plastic dividers to customize the compartments. The repair kit also has a QR code that opens the standard servicing procedure for that equipment. The main purpose of the repair kit is to save time, but it also saves money. When I repair something for the first time, I typically purchase 1 or 2 extra spares. This guarantees that the next time the problem occurs, the repair time is reduced from days to hours. Having spares available once saved me from a potential 3 months downtime, because when I tried to order the spares, it was out of stock and it needed to be made at the factory. I also have tools in the repair kit. Common tools like screwdrivers and wrenches are available in the general toolbox, but I've wasted so much of my life looking for tools when I need them. This repair kit also contains special tools such as a trim pin cut to the right size, custom pneumatic line cap, super glue, tweezers, and so on. I wasted several days trying to adjust a trim pot with a flathead screwdriver and only learned about the trim pot pin after ranting to the technician. Common sense to a professional technician is not common sense to a lay person. So a good way to share these tricks of the trade is through a well-written SSP. Some parts can be expensive, such as vacuum pumps and chillers. For this situation, I decide on a pump that works for our equipment, make it standard, and buy one as a spare. When other pumps fail, I replace it with the standard spare and buy another one. After a decade of doing this, our pumps and chillers are interchangeable. This allows any pump or chiller failure to be resolved within an hour by replacing it with a spare. Then I can take my time to repair what will become the new spare. You know what's better than repairing? How about not needing to repair? Sometimes equipment break or fail from operator errors. Operators do not intend to make mistakes, but mistakes happen. The most common mistake is simply not knowing or forgetting what to do. The best way to avoid operator error is to provide a high-quality standard operating procedure, or an SOP. Since we implemented our SOPs, we have effectively eliminated operator errors. Our SOPs have helped users successfully operate complex scientific equipment after months or years of hiatus. That's right, after the initial training, we do not require users to get retrained when they become inactive. If you're interested in our SOPs, we have a video about it in our channel. Sometimes you are repairing because the equipment has a glitch or a bug that leads to malfunction. For example, wafer jam occurs approximately once a month, which takes 1 to 5 hours to repair. Sometimes it is caused by operator error, but most of the time it just happens. We think it's because the wafer wobbles out of position while it's being loaded, so we replace those two alignment pins marked in red with a custom-made wafer holder. This modification effectively eliminated wafer jams caused by the equipment. We also modified the wafer clamp, which greatly facilitates alignment and reduces the repair time to 1 hour max. A secret benefit of self-repair is familiarity and comfort with the equipment. This allows us to tell students during our facility orientation that they should wean off following our SOPs as soon as possible, and there is no penalty for making a mistake. It is far worse for society when a person who acquires a PhD needs to use an SOP in order to operate equipment. Since we are confident that we can repair 99% of operator errors quickly and cheaply, we can provide our students a better environment to learn and develop. Last but not least is monitoring equipment health and establishing a preventative maintenance program. Although UHNF opened in 2009, we didn't regularly monitor equipment health until 2020. When I read the routine maintenance for our etcher, it was overwhelming with recommendations for weekly, monthly, 3-monthly, and annual checks. I used the recommendation as a reference to establish a checklist for our tool. I started monitoring various health indicators monthly, but realized it is okay to check every 3 months. The frequency to check depends on the rate of change from a healthy level to an intervention threshold. I have developed a dashboard on Google Sheets that highlights in red when a health parameter needs intervention or needs to be checked. This graph shows the oil level for the chamber pump for our etcher. This pump loses oil at a rate of approximately 1 pint every 3 months. This oil costs $200 per pint, so we spend approximately $800 a year on oil for this pump. Analyzing the health trend can help us make preemptive repairs. This pump doesn't leak, and it has an exhaust filter that recycles the oil. We don't know exactly why we're losing oil, but it is currently much cheaper to pay for the lost oil than to buy a different pump that may or may not solve the problem. Self-repair is risky at first, but doing it well provides many benefits to society. At UHNF, we significantly reduced our operational expenses by repairing our own equipment. Since we have a stock of spares, approximately 95% of issues are repaired within 2 hours. Many of our equipment are nearing 20 years old, but their performance is as good as new. Some of our tools are arguably better than new tools because we have optimized processes that would take years to recreate. I will talk more about this in a future video about process development for nanofabrication and our publicly accessible process database. The greatest benefit of an SSP is that it significantly reduces the risk of self-repair. A new person can review the entire repair procedure to determine if the procedures are comfortable. Since it is written by someone who successfully performed the repair, it means the procedures are safe for the operator and the equipment. Finally, it ensures the repairs perform consistently no matter who is doing it. Frankly, some issues occur so infrequently that I sometimes don't even remember that I've repaired it before. In such cases, I feel extremely grateful to my younger self who put in the time and effort to save the future me time and resources. To further reduce the barriers to writing an SSP, I have written an SOP to write an SSP. I also share most SSP I've written to folks who own the equipment. You can use it if you have the same equipment or learn from it. I have provided a link to our SSP in the description of this video. Ideally, equipment manufacturers would develop, maintain, and provide SSPs. I haven't convinced any company to try to make SOPs or SSPs yet, but I'm confident it's the future. I hope this presentation has encouraged some of you to write an SSP. Thanks for watching.